Okay, so the name of this talk is Hiding in the Clouds, and a little bit of background on this talk is that I was working on an engagement. It was a fairly large engagement for a financial client that they wanted an evasive test on, but this was a massive scope, and this kind of caused me to look through different techniques and procedures that would allow me to, at scale, perform evasive testing and non-attributable testing. So in this talk, I'm going to go through the various techniques that I found and developed, and it's gonna get pretty interesting. So let's hop right in. A little bit about me. I'm a senior consultant at Evasive Security. Also, I try to be a full stack developer. Kind of fail at times, and I got some alphabet soup next to my name. First of all, I'm going to go over the cloud, and the cloud really started in early 2000s and in 1999 when Salesforce delivered the first application purely via the cloud. And then when in the 2000s when Amazon realized they had all this extra computing capacity but didn't really know what to do with it, and that pretty much created AWS and what we know is the behemoth that has become today. From there, it kind of cued a revolution of now everything's in the cloud, whether it be DevOps, basically application delivery, you name it, it's now going to the cloud. So another question to ask is, why would you want evasive testing for a penetration testing engagement? There's really two facets to it. One is you want threat replication, because oftentimes, pretty much every time, right, attackers are not trying to be caught. They're trying to evade the detections you have in place on the perimeter or on your internal network. And through evasive testing, you can get an accurate idea of whether or not your defenses are actually picking up this activity. And that goes to improving your defenses, because if you're not picking up obvious activity or even slightly evasive activity, then you can go back and review that activity and tune your defenses to pick up this stuff and work with the attackers, or work with your testing team in order to improve your defenses in that aspect. So now I'm going to move into web application attacks via the cloud infrastructure. The first and most obvious aspect of this is proxying web traffic. This was mainly used for the discovery and exploitation phases of a penetration test. And a lot of the times I use it for brute forcing, and whenever I'm blocked, it's really not a problem because you can either bring down your service, spin it back up, you have a new IP address. Thus, you've evaded any blocking going on, and they can't really correlate your traffic to one specific endpoint, and your infrastructure is constantly moving. Also, there is a nifty thing called an API gateway with Amazon. This API gateway allows you to make requests to a gateway that you set up, which then basically proxies those requests to a specific endpoint. And this is an example of me doing a OWA, Outlook Web Application username guess or password guessing. And this is a very common attack on penetration tests. But this way is that with the API gateway, each request is generally coming from a different IP address. So per region, you have about 550 approximately different IP addresses that it can come through. So what I have here is that you can see, y'all see the host header right here? Maybe a little bit? So the host header you see is execute API US blah, 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 right? So that's kind of what I'm making my request to. Thus, my client is making a request to Amazon, while Amazon is then making the request on my behalf to this OWA portal. And I'm receiving the valid responses at the top with those longer lengths than the 897, the 23271. Those are valid login, or basically successful login attempts. So I was able to use the Amazon API gateway to now log into a client's OWA gateway and then go ahead and basically go from there and completely obfuscate my attack. I'm going to save questions until the end. Yeah, it's a very useful tool in attacker's toolkit, and it's something that defenders need to be aware of. If you're seeing a lot of requests from Amazon, it's definitely something to look further into. Next, we're going to go into something that has become kind of a hot topic lately. One of my favorite things to work with is domain fronting. And for those of you that don't really know what domain fronting is, it's really a technique that basically using the major content delivery networks to bypass internet censorship. So from the beginning, companies like Signal would use it to bypass restrictions. Like during the Arab Spring in Egypt, they used it to ensure basically application delivery to their users by using the major content delivery networks such as Akamai, Google, and Amazon. It allows them to use their infrastructure to deliver their application without actually requesting the infrastructure of Signal. You can actually make a request to something like google.com or instagram.com, and through that you can tunnel your traffic through those channels. One thing is that stopping it does tend to break a lot of things, as you may have seen in recent days with the Google basically destroying domain fronting on Google App Engine, that it kind of hurt a lot of Signal users. So the real question is, why do you care about domain fronting in terms of being an attacker or even a defender? Because it really is useful for bypassing egress controls. And most of the communication is done over SSL. So this means, as a defender, you have a potential for legitimate-looking web traffic to be communicating over SSL, leaving your organization and right underneath your nose. So it's really something to look into, and I will go over mitigations further along in the slides. But the last point is probably the most important one, is that domain fronting tends to use very popular domains that are very common to see in an organization, which I'm going to go into in the next set of slides. But who's affected is basically all of the major cloud providers, because it's just the way that these content delivery networks work. So it's really just it's an availability feature. It's not a bug. So it's something that can be abused by attackers for exfiltration, but it also provides greater availability for the internet as a whole. So it's kind of a double-edged sword. So I'm going to go over basically an example of domain fronting with Google App Engine. And what I'm going to be using here is TLS proxy application in Google App Engine. And the key thing to note is that it leverages google.com domains. So any star.google.com domain you could have used for domain fronting. Google decided to kind of be jerks about it, and right before I was about to go on vacation, break this whole thing for me. So please excuse any dated information. So one thing for domain fronting, you need a C2 server. In this instance, you need a Google Cloud account, a redirector program to deploy and redirect requests back to your infrastructure, and the C2 configuration with a host header that actually goes back to your infrastructure. Because what you need to understand about domain fronting is that the request domain, let's say I'm using Amazon CloudFront, for example, which is a popular domain fronting. I make a request to Instagram.com that's on CloudFront. So my request and my TLS negotiation happens with Instagram.com. So when that request reaches the infrastructure of Amazon, that URL is taken away because it's reached its destination. It then reads that host header. The host header actually doesn't go to Instagram. It goes to my CloudFront instance, which then redirects back to my C2 infrastructure. So now, from a defender's perspective, they are seeing a TLS negotiation with Instagram.com, then they are seeing encrypted traffic between Instagram.com. Little do they know that all of this is C2 communication between my infrastructure and my target system on the internal network. And this is just a Cobalt Strike configuration for basically for this App Engine instance, the host header that host thing is going to be your host header. And this is the big thing, is that where my beacon or my agent is checking for taskings or checking for commands, it's going to be checking to inbox.google.com. And let's say in my Instagram instance, it would be instagram.com. So it's very kind of perplexing to say that my C2 will actually be checking for taskings from a very popular domain. So here we have an example of a Cobalt Strike PowerShell payload being run and then executed. And then the second screenshot you see is it grabbing the stager and then going ahead and getting the beacon to run in memory. And then finally, we get a beacon back to our Cobalt Strike team server. And this is a Wireshark capture of the communication on the client. So what you can see here is that the certificate negotiation and key exchange are happening with the Google certificates. So this is a valid Google signed TLS connection. And that's one of the biggest things about domain fronting, is that you are negotiating your TLS connection with the popular domain. So one of the reasons that Google really, in my opinion, they don't say so, but that they killed this technique, is that now many organizations whitelist Google leaving their network. A lot of that is due to host strict transport security on a lot of Google domains, and that would basically allow me using Google domain fronting to go ahead and have a free pass out of an organization without any of the traffic being inspected or having the TLS stripped, which in my opinion was a very big problem. So this, in my opinion, it was good that they fixed this issue. It was a little bit of a bummer from an attacker side, because I love to use it on internal evasive engagements because it was very successful. However, keep in mind from a defender's perspective, this technique is still very widely available with other providers such as Amazon, Azure, Alibaba, and many others. So it's something that as a defender, if you're defending an internal network in a highly sensitive environment, definitely take a look more into this technique, because it's something that advanced adversaries are using in the wild today. And here's the good stuff. So one of the mitigations, you can do SSL stripping depending on the domain that it's negotiating with. Most vendors can't do Google, which was probably why it's good that Google fixed this issue. But a lot of these other domains you can inspect, and then you can look for anomalies in the traffic from there. Also, having an RFC 2616 compliant proxy will actually rewrite the host header in order to match the requested URL. So if your traffic is going through a proxy, but it's not RFC 2616 compliant, then it will not stop domain fronting. But if it is, then that will essentially eliminate this technique. Also, one thing to look for is that a lot of the tools today, they do a handshake with each request out and with each communication with the C2. So looking at the ratio of SSL and TLS handshakes to traffic is a strong indicator that domain fronting is occurring. The closer you are to a 1-to-1 ratio, the more anomalous the traffic will look, and that's something that should be investigated. And finally, the most obvious one is just knowing your general network baseline of what URLs are frequently visited, if there's anomalous traffic at different times of the day, and just knowing what's going on inside your network. And that's obviously one of the harder ones to do, especially in a larger organization. Next, I'm going to move more into techniques that involve more automation. Ephemeral infrastructure is kind of a technique, or more of a ideology that I've kind of been working with a lot more. This leverages the global nature of cloud infrastructure and the fact that you can use many different providers to create in basically how would I describe this? An attacker infrastructure that spans the globe and spans multiple different IP spaces that can be rapidly deployed and destroyed, thus creating a very small footprint for your actions. This means that I can perform 20 web requests on this server, bring it down, and then spin up on another provider on another side of the globe and continue my attack. This makes it hard for attribution because of the constantly moving nature of this, basically these techniques and procedures. And also, this leads to really small footprints that makes it very hard for investigations and trying to tie this back to any single entity, just because leaving anything on the internet leaves it constantly exposed to attacks every day. And one tool that I'm releasing at Black Hat Arsenal this year is going to be hide and sneak, and this leverages a lot of these techniques and provides an easy interface to spin up and destroy and manage all of these different cloud products very quickly and rapidly, which is kind of different than the traditional red team management tools that are out there, such as like Red Baron. Furthermore, you can also use proxy chains with a lot of effectiveness here. So if you're spinning up a lot of servers, you can put basically SOX proxies on these servers and use either SOXD or proxy chains and their randomization options to randomize each request coming out of these servers. So let's say I want to run SQL map, I can run it through 50, 100, 150 different servers across different providers, and all of these requests will be going through a different server each time. So that makes it, again, very hard to identify and correlate traffic to one entity. There are drawbacks to this technique, though, and it's very slow. So that's what led me to this next technique of distributed scanning. This allows me to basically have a global infrastructure where I can distribute scan jobs and have a very evasive nature to port scanning. Because a lot of the times, port scanning is one of the first things that will be picked up by an IDS, IPS. Because it's very, very easy to identify if someone's scanning a range of ports or even randomly scanning ports. But with what I've been doing is that I will get a range of IPs, a range of ports, make a combination and enumerate all the different combinations of each into a list. And then I will assign each one randomly to, let's say, 100 different servers across different providers and around the globe. And so now each server is scanning one port on maybe 3 or 4 servers at a time, and it splits up everything. And it slows down the scan, and thus really evades the detection of most products on the market today. And even with that, the possibilities are really growing in terms of the cloud products being offered as more things such as Lambda functions become available. The possibilities for attackers to leverage cloud infrastructure to pivot and create small footprints is growing exponentially. And it's really something that, as defenders and attackers, we both should be looking at and seeing if we're prepared to use these or defend against these in our current environment. And that's the end of my talk, and I want to thank you for coming here today, and I really appreciate it.